Aurora is also known as the Aurora Borealis for the northern hemisphere aurora, and then the Aurora Australis for the southern lights, if you like. So this effect happens in both the north and south because the effect is due to the magnetic field of the Earth and the fact that we have an iron core which is magnetic, and this magnetic field is strongest at the north and south pole, which is I guess why why your compass works and things like that. So in terms of kind of human exploration of the aurora, we know a lot more about the kind of northern aurora just because there is a lot more humans that live kind of in the north of the Earth, and obviously there isn't that many people who live in Antarctica. So we know more about the northern lights, but we have cameras in space that are looking at both the north and the south of the Earth, and kind of taking images of it regularly. The northern lights is produced by, it's basically just photons of light in our atmosphere, and these photons of light are a result of the air in our atmosphere, which is getting excited by charged particles from space. Most of these charged particles, protons and electrons, are from the sun and the solar wind, which is constantly throwing out material into space, and then it kind of hits the atmosphere. You get a kind of cascade of, energetic particles, which means that suddenly you go from having nothing overhead to this very kind of green, bright auroral display. And the features you see, the shapes here, are kind of tracing the magnetic field. So that is why, as physicists, we are interested in looking at them. And in Southampton, we're not necessarily looking at the kind of large scale structure, so that this massive like arc over the top of the sky. We're kind of closing in with our camera on a very small part of the aurora where we know there is a strong magnetic field, and trying to see how that structure changes on a very small scale. So it's always looking at the same point, basically, above the sky in Norway. So the aurora isn't like a static thing. It is dynamic, it is moving. And here you can see in this video lots of what we call curls and swirly things that are happening on these small scales in this camera video of the aurora. Like I said, it is produced from the sun. So as well as the Earth having a magnetic field, the sun has its own magnetic field. And in this video, you can see these things called prominences, which are kind of, again, tracing out the magnetic field. So you can see it with your eyes, basically, of the sun itself. So when there is what we call kind of reconnection events, or when the magnetic fields kind of hit each other and snap, they will eject lots of charged particles into space, and they will be some of them will be attracted to the Earth because of the Earth's magnetic field. And the solar wind actually drags a magnetic field with it. So this is why this can be quite harmful to satellites and things like that, which get in the way of the solar wind. This is an image from the SOHO spacecraft, which is constantly looking at the sun. So the kind of circle here is obviously blocking out the sun, so it doesn't kind of bleed into the camera. And in a minute, you'll see a massive flare. And then a few seconds later, when it reaches the camera, you will see lots of kind of white noise and static on the camera, where the camera has so much kind of, I guess, photons and electrons coming towards it that it interferes with the actual thing. So you can see it in a minute. So that was the big flare. And then I think a few seconds later, then you see and that really shows you the amount of interference you get from these solar flares. So we do our best to protect our satellites and things in space from solar flares, but we really can't do that much, because obviously we can't control what is going on in the sun. We can just do our best to protect things. And again, luckily for us, the magnetosphere around the Earth does protect us a lot from all these charged particles from the sun. Otherwise we would be, toast, let's say. So this is just a very, well, obviously an artist's impression. This is not to scale by any means, but this is a good graphic to show you the magnetosphere, which is around the Earth. So it isn't symmetrical. It's kind of because of the magnetic field of the sun, which is kind of constantly pushing on it. This side of the magnetosphere is squashed, and then you have this thing out here called the magnetotail. So there's a kind of common misconception that the particles from the sun, they kind of travel through space, and then they are attracted to the magnetic field lines, which are kind of anchored onto the top of the Earth, and then the particles just flow down, and then you get the aurora here. But what actually happens is the particles get trapped in the magnetosphere, which is represented by this kind of green blobby stuff here. And then when there is a magnetic field which is dragged along with a big coronal mass ejection or a solar flare, it kind of pushes into this magnetosphere and causes all this plasma then suddenly, very, very quickly, suddenly then go from being trapped here to being on top of the Earth and visible. And I think there's a video next to show you that a bit better. Okay, so you have obviously the sun constantly giving out charged particles into space in all directions. And then, wait for it, you have this solar wind. So you can see that the field of the solar wind hitting the front of the magnetosphere, and it kind of wraps around, causes the magnetotail to the field lines to come closer together. Then they have what we call a reconnection event, snaps all the plasma around, and then that feeds onto the top of the Earth and makes this little kind of crown here, which is actually called the Auroral Oval. And where things that are at that latitude or longitude on the Earth, where you see this little kind of red crown, is where you would see the aurora. So if you're maybe thinking, well, actually, people in Southampton in astronomical societies, they've actually said they've seen the Northern Lights, and that they're not like crazy. It is possible if there is enough material kind of trapped here in the magnetosphere, and it lands on the Earth and gives this kind of auroral oval enough energy, if you like, it will actually move more down to the south. So you can see the aurora in Scotland, in Southampton, places much further south than normal. But you need to keep track of all these aurora websites, which kind of model what the shape of the aurora is as it sits kind of on top of the Earth. So you could see when you're likely to be able to see it from where you are, basically. So I don't know if you still do this experiment in school or college these days, but I certainly did it. So you get iron filings and you've got your bar magnet, and the iron filings directly trace out the magnetic field, and where the iron filings are kind of closer together is where your magnetic field is stronger. So this kind of principle is exactly what is happening in our Earth, which is why we're mainly getting the plasma kind of coming down into the north and the south. From our cameras that are out in space, we can see that it's actually quite symmetrical what happens. So that kind of the shape and the features of the aurora that we see from like near the north are the same as what happens in the south, but at the same time. We have two excuse my dog barking. You have two cameras that are looking at the same time at the north and south of the Earth. They see very similar features. So that is quite cool, because obviously the Earth is really big, but the magnetic field is symmetrical. And just an aside, the magnetic field lines are not in line with the kind of axis of the actual Earth. The geographical North Pole is not the same as the magnetic North Pole. So this is how you would see the aurora from space. This is specifically taken from the International Space Station. And because the International Space Station is higher up than the level of where you get the aurora, well, you can see it absolutely filling the dome of the Earth, and you see a lot more of the red aurora, which I will explain shortly. But yeah, but obviously very few people have been lucky enough to see the aurora from space. Okay, so how high is the aurora? So the aurora is about, well, basically between about 100 kilometers altitude and like height above the Earth and 300 kilometers. So it's quite a big kind of volume of our atmosphere. It is below the International Space Station, which I just showed you, which is about 340 kilometers up. And therefore planes are below the height of the aurora. The main thing to note is obviously that the satellites are basically at 200 kilometers, which is smack bang in the middle of where you get the aurora. And the aurora is actually dumping kind of large amounts of energy when you get this kind of solar, the plasma coming in to the Earth's atmosphere. So you will get kind of static interference and things from those satellites which are in the region for sure. But also you want to kind of allow for the fact that that energy that is entering into the atmosphere will actually potentially have an effect on the weather, which is kind of where the Met Office consider or care about. They didn't used to care about anything above 100 kilometers, but they have started to kind of communicate with the space scientists and understand that space weather can have an effect on our kind of weather that we see on the Earth. So they don't think it's necessarily got anything to do with climate change or any of the really kind of big issues to do with the weather, but they are kind of, when they're modeling the weather, they might take into account if there is a big solar storm, for example. So if you're looking down on the Earth now, so the North Pole is right in the middle here. This is this green circle is representing kind of where you would see the aurora. So it's what's called the Auroral Oval. So it's important to note that there is a gap in the middle. So the actual geographic North Pole, which is here, which doesn't actually have any kind of land, you wouldn't actually be able to see the aurora from the North Pole typically, because of this, the way that the magnetic field actually anchors onto the top of the Earth. So the places where you're most likely to see it are kind of, well, Finnish Lapland, where Santa lives, kind of Norway mainland, Svalbard, which is where I went, which is still part of Norway, but you can see is much further north than the mainland Norway. And then you've got aurora visible in Greenland, Canada, and Alaska, and Siberia. And the reason why it's interesting to go to Svalbard to look at the aurora is because it's right on what we call the cusp, the edge of this auroral oval. So there is some quite interesting physics which is happening right on the edge, because it's where this last part of the magnetic field is usually anchored onto space. But yeah, again, this auroral oval is never a perfect kind of circle like this. It is an oval shape, and it varies in kind of size and position depending on the amount of plasma that is kind of being forced onto the top of the Earth. But the scientists, when we were in Svalbard, were looking regularly at a screen which had this oval on, and then we could see if we were very likely to have the aurora above us where we were in Svalbard. Okay, so I've already kind of talked a little bit about this, but just again, another little aside is that the actual magnetic North Pole is at the bottom of the Earth, where we have the geographic South Pole. So I forget how long it takes, but there will be a time where the magnetic field of the Earth flips, and the geographic north and the magnetic north line up. But to be honest, for us on the Earth as humans, it won't really mean much to us. It'll just mean the field lines go a different way, so it won't really have any influence on our kind of day-to-day lives. So this is showing you again from above, but you can see this is the red lines are kind of where you expect the aurora to be, and then the green oval kind of more kind of blobby shape is where it actually is likely to be at this time, based on the data that we have from our telescopes and things like that. So I could see potentially at this point, based on this image, where I was in Svalbard, I'm maybe unlikely to see any aurora at that particular time. Okay, so the color of the aurora is due to, well, depends on which element in the air is getting excited by these electrons from the sun or from space. So we have 2 electrons here, and these are representing all the different particles in our atmosphere, in the air above us. And as the electrons from space come in, they will hit some oxygen. There is a lot of oxygen higher up because it is lighter, well, with respect to nitrogen at least. The oxygen gets energized by the electrons, and then will emit a photon of a certain energy. And the oxygen that is higher up receives quite high energy electrons, so is able to give off quite what we call high energy photons, which turn out to be red. So the higher up aurora you see is a result of oxygen, and that is red. You can get some interactions with nitrogen, but there isn't too much nitrogen that high up. And then as you go further down, you can excite the kind of lower energy bands of oxygen, which are green. Now, when you excite these atoms, you also have ionization happening. So they give off electrons, and then that is how you get this kind of cascade of electrons. And suddenly the sky goes from being quite dark to suddenly very, very green. So we mainly see the aurora as green because the rods and cones in our eyes are very good at detecting the green light. So it's very rare for you as a person on the ground to be able to see red aurora, just because of your eyes, but also because the red aurora happens at a much higher altitude. So you can see it when you're on the International Space Station. But also it just means if you go and see the aurora, if you're lucky enough to go and see it with your eyes, you might be a little bit disappointed because it doesn't look, the colors don't look as vivid with your eyes as they do in photos. Because when you take a photo of the aurora, you can do a long exposure, for example, and the charge couple device, which is in your camera, it is able to just pick up some more of the colors. So it does look green. Obviously, I've seen it now with my eyes on the expedition, but it doesn't look as green as it does in the photos. Okay, so as we get further down, closer to the Earth, then there is a lot more nitrogen. And when the nitrogen is excited, then it is a kind of blue or purple color. This is very rare to get a blue or purple aurora. But my friend who lives in Finland, she has seen a purple aurora only once in her whole life, and she lives there. So yeah, shows you how rare it is. But yeah, like I said, the main green light is from the oxygen in the air. So I think I've basically said most of this. But yeah, you have above the 250 kilometer mark is where you get the red aurora occurring. And I kind of hinted towards this, but this is basically why you can get the green light and the red light both from oxygen. It's just representative of a photon that's released by an electron jumping up. So if the electron is able to kind of jump back up to a higher level, so kind of go past 2 shells, then it will release a photon that is red. But if it's only one of these smaller energy jumps, which is just kind of 1 shell, then it will give off green. Okay, so a similar thing happens with lightning, but because lightning is traveling through the air, which is much closer to the Earth, is finding a path from the clouds to the ground, it has to go through nitrogen. So these charged particles travel through mainly nitrogen, which is why lightning looks kind of blue or purple. We also get the aurora on other planets, and the University of Southampton Space Environment Group, they are quite active in looking at the aurora on Jupiter and Saturn from their telescopes in space. And obviously they're tracking the kind of shape of this aurora from above to learn more about the magnetic field of these planets.